The space station, another step in the continual building process, where each venture into space forms the foundation for exploring the universe. As man strives to reach new heights in space exploration, he must first develop the skills necessary to successfully live and work in the zero gravity of space. The year is 1973. America's first home in space, Skylab, is in orbit. Throughout the 3 Skylab missions, flight crews conducted a variety of experiments in medicine, Earth observation, engineering, solar physics, and astrophysics. The technology developed during Skylab provided the basis for the design and development of future long-duration space stations. In addition to providing a laboratory for important studies, Skylab marked a significant transition in the spaceflight program. In each Skylab mission, we became workers rather than observers. Skylab also provided a testing ground for techniques and equipment which would be needed for man to work effectively in space. One of the tools tested, the astronaut maneuvering unit, would prove its usefulness on future flights of the space shuttle. February 1984, the 11th mission of the Space Shuttle program, Mission 41B, is in orbit.
4 miles a second, Bruce.
The astronaut maneuvering unit tested on Skylab is now called the Manned Maneuvering Unit, or MMU. Its first checkout in space is about to begin.
Okay, here we go. Well, that may have been one small step for Neil, but it's a heck of a big leap for me.
Copy that, Bruce. Thank you.
Oh, this is really beautiful out here.
Here, McCandless was 300 feet out from the spacecraft. He had proven the manned maneuvering unit could be flown in space, and he simulated something very important. He traveled the same distance another astronaut would have to travel 2 months later to get from shuttle to an ailing NASA satellite.
204 feet.
On the next shuttle flight, the satellite called Solar Max would be picked up by the shuttle, repaired on orbit in the payload bay, then returned to space.
Marvelous machine.
Solar Max was launched from Kennedy Space Center, Florida on Valentine's Day, 1980, in the year of the solar maximum, the 1 year out of every 11 that the sun is most active. But within 9 months, Solar Max had developed serious problems.
The Solar Max repair mission was a very interesting experience from a number of points of view. For some number of years, a team of people at the Goddard Space Flight Center had championed the idea of designing satellites so that they could be repaired on orbit or retrieved and brought back to Earth for repair. It was a chance to demonstrate the kind of things that both the Goddard people who designed the satellite and we who operate the STS had been saying, that is, that we can do these things on orbit. Satellites that are designed to be repaired on orbit can save a great deal of money because we don't have to bring them back, we don't have to launch them again. Building things so that they can be fixed is going to become a byword of the satellite and space station design of the future.
In fact, one of the main reasons for the 41B mission was to test the tools and techniques that would be used to repair Solar Max on the next flight.
The plan to capture, repair, and re-release the Solar Maximum spacecraft had been over 2 years in the making. One of the essential elements of this plan was to use the maneuvering unit and this device mounted on the front, known as the T-pad or trunnion pin attachment device, to capture an existing hardpoint on the Solar Maximum spacecraft and to stabilize it for RMS retrieval and repair. In order to lessen the mission risk to the subsequent mission, 41C, we were assigned the task of conducting an MMU test flight and of proving out the trunnion pin attachment device function on our flight. In addition to the activities with the manned maneuvering unit on STS-41B, we had another important piece of equipment to evaluate for the first time, the manipulator foot restraint. The manipulator foot restraint is analogous to the cherry picker that construction and power line crews use, and is basically a foot platform with ski boot-like bindings that you can lock your feet into, that mounts on the end of the remote manipulator arm and can be positioned anywhere in the cargo bay area and holds you in a firm, stable position without expending propellant, as the MMU is required to do, for hours at a time. The manipulator foot restraint carried tool boards equipped with tools such as this modified power tool. On the backside, additional simple hand tools. And I exercised this against a mock-up of the electronics unit and some of the other detailed mechanical tasks that were to be performed by Ox Van Hoften and Pinky Nelson on the subsequent STS-41C flight.
Challenger Houston, at this time, West Star is go for deploy.
Roger, we'll go for deploy.
Unfortunately, Flight 41B was also the mission on which the West Star and Palapa communications satellites failed to reach their expected orbits.
Challenger Houston.
The deployment of both satellites from Shuttle's payload bay went off without a hitch, but the rocket motor nozzles failed, causing the thrust to be dispersed. Without propulsion, the satellites could not reach transfer orbits.
So we had to explain the difference in what the NASA responsibility was and how the part of the mission during which we had this failure and the equipment that was represented in that failure was really the responsibility of the communications satellite customers that we were flying. NASA provides the shuttle ride, and the customers design, build, and pay for their own satellites and upper stages, somewhat independent of NASA.
April 1984, Shuttle Flight 41C on orbit, having rendezvoused with the Solar Max satellite.
Challenger Houston through Hawaii, and we've got a good picture of Pinky flying in the bay.
Copy that. I'm just doing a little getting some hands-on time, Jerry.
Roger, copy that, and ground's giving you a go for the MMU flyover, and the POX commanding is inhibited until we're on the FSS and tilted.
One potato, two potatoes.
Maneuvering unit pilot George Nelson made his way over to the satellite. Commander Robert Crippen, pilot Dick Scobie, and mission specialist Terry Hart monitored his progress and the progress of James Van Hoften, waiting in the payload bay. Nelson was having trouble docking with the satellite. The T-pad was not locking onto the trunnion pin, and his attempts were causing the satellite to wobble. His maneuvering unit propellant level was also getting low. He would have to return to the shuttle. Solar Max would have to be grappled instead with the shuttle's robot arm. Nelson headed back in while the crew on board prepared to capture Solar Max. The shuttle was out of range of voice and picture coverage, while Bob Crippen maneuvered the ship and Terry Hart tried grappling the satellite with the robot arm. On the ground, mission controllers anxiously awaited word from the crew. Minutes went by before they got the news. The grapple didn't work.
Of course, we were very disappointed we didn't get it. We'd been training for a year, and all of a sudden we were missing it. We ended up, after that fourth attempt that we made, and we still missed, and we were getting real low on fuel. That was when the ground told us they thought that they might be able to stabilize it from the ground. So we backed away and turned it over to the Goddard Space Flight Center in Greenbelt, Maryland. The main thing that we had a problem with was, since it was wobbling, it wasn't pointing the solar rays at the sun. Consequently, the electricity was going down and down and down.
Goddard immediately went to an alternate plan for restabilizing Solar Max. A new attitude control program was transmitted up to the satellite's onboard computer. To give as much power as possible to this new stabilizing attempt, Goddard turned off all the heaters, the instruments, and everything else not essential to the stabilizing effort. Solar Max was entering a crucial eclipse on the dark side of the Earth. When Solar Max emerged, its power was almost gone, but it had stabilized considerably. The method worked. The next time controllers checked, the satellite had stabilized even more and moved into a position that exposed the solar panels to the sun for a brief 10 minutes. When the crew awoke from their sleep period, Goddard had presented them with a Solar Max that was ready for capture. Crippen could now move the shuttle toward the satellite for another grapple attempt with the robot arm.
This is Mission Control, Houston. Loss of signal at the tracking satellite. The remote manipulator arm was in motion at the time of loss of signal.
Challenger Houston standing by through Yargity.
Okay, we've got it, and we're in the process of putting in the FSF.
Outstanding.
With Solar Max secure in shuttle's payload bay, the repair could now begin.
Buggy up a little bit more and a little bit more towards the satellite. Got plenty of room towards
The first order of business, of course, was to change out the attitude control system. That was the main thing, to repair the satellite.
I don't know, Peggy, that trunnion pin may be...
Next, we attempted the main electronics box, which is a major part of one of the prime experiments. That night, the ground went through the checkout of the satellite to make sure that it was working properly.
Challenger Houston, you go for release as long as you're within 5 degrees.
Roger.
The next day, we redeployed the satellite with the attitude control system and all 7 of its experiments working properly.
The first retrieval and repair of a satellite in space had been a success.
The Solar Max repair mission was a great achievement. It was an example of planning to do something and finding that the primary method of doing it, that is Plan A, didn't work. We had to call upon Plan B during the course of that flight.
The fact that 41C was a success strongly influenced the decision to make 51A a mission which would rescue the Palapa and Westar satellites. An interesting aspect of this mission was that NASA did not own the satellites. The insurance underwriters owned them.
So what was new for us was that now we had a new party involved in the discussions, in that the ownership of the satellites was in fact the insurance underwriter in both cases. So we had a set of discussions in Washington, primarily at our headquarters level, where the details of working out the agreement as to who would pay for what and how much NASA would charge the underwriters gradually developed over a period of time.
A crew was named and began training as a team, with equipment designed and built specifically for the rescue of Palapa and Westar. Perhaps one of the most important elements of the retrieval operation was the Apogee kick motor capture device, or Stinger as it was called. It was the tool the astronaut would use, together with his maneuvering unit, to capture the satellite, stabilize it, and bring it back to the shuttle. Hughes Aircraft Company had to begin the complex job of maneuvering the satellites into position before final negotiations with the insurance carriers could be completed. Otherwise, there would not have been enough time to place Palapa and Westar in the precise position, in the precise orbit, at the precise time for rendezvous with the shuttle. On November 8, 1984, the shuttle and its crew of 5 set out to rescue Palapa and Westar. Palapa was there. Hughes Aircraft Company had lived up to its end of the bargain.
Holy mackerel. I am not 20 feet from that satellite. You got about...
Maneuvering unit pilot Joe Allen flew over to dock with Palapa, while Commander Rick Houck, pilot Dave Walker, and mission specialist Anna Fisher monitored his progress and the progress of Dale Gardner, waiting in the payload bay. Alan inserted the Stinger device into the satellite, docked, then, using his maneuvering unit, stabilized the satellite. Fisher moved in with the robot arm
Get in there and grab that thing. Just go get it, Anna.
and brought Alan and the satellite back into the payload bay. There, Gardner attempted to attach the A-frame device to the satellite. The A-frame had a grapple fixture installed on it to be used by the robot arm to hold the satellite, while Gardner and Alan attached the support structure to it. The support structure was used to secure Palapa in the payload bay for its return to Earth. The shuttle went out of range of voice and picture coverage as Gardner attempted to attach the A-frame.
Houston, Discovery, we're going to let Dale talk. We got a problem here.
Discovery, Houston.
Okay, Jerry, here we go. The common bracket clamp will not fit on the satellite. The problem is, between the two octagons, between the two common bracket parts of the satellite, is a structure that's sticking out far enough that it is hitting the cross brace of the common bracket clamp, and it's not a piece of structure I can remove.
Okay, understand that, and what are you proposing to do?
We are proposing to go to the no A-frame procedure, and I will go up to the PFR in the forward pallet and try the technique perfected by yourself.
Okay, we copy Plan B and proceed.
Okay.
Plan B was a contingency procedure that astronauts Jerry Ross and Pinky Nelson came up with 1 week prior to launch. Unlike Solar Max, Westar and Palapa were not designed to be retrieved. The customers didn't intend ever to see these satellites again, so there was no need to pay for extensive documentation. As a result, mission planners had to anticipate that the drawings would not illustrate all the details.
So Joe, upon learning that indeed we're going to Plan B, had to detach himself and the backpack from the satellite, fly into the bay, stow the backpack, and come over and get into a foot restraint into a position such that he would now be able to hold the satellite with his hands. So the Plan B that we chose was the one that required Joe then to take the place of the robot arm to hold the satellite himself with his hands, while I performed the functions that needed to be done on the other end of the satellite. And then finally, when that was all done, for us together to berth the satellite into the payload bay, the other function that the robot arm would normally do.
Okay, yes, Joe, you can move across.
If you got two, you can latch the third, guys. You ever ready back there?
3 latches down and locked.
Oh, my goodness.
Mission elapsed time 4:05:57:43.
All right, we got her.
The first satellite was secured in the payload bay, but it had not been an easy task. Perhaps Plan B could be improved upon. There was a one-day intermission between the Palapa and Westar retrievals, so Jerry Ross and Pinky Nelson went back into the water tank at the Johnson Space Center where they first developed Plan B to see if it could be improved upon.
But the major difference was I would hold the satellite from a position on the arm, the robot arm. And that enabled us to work in the vertical without getting near the satellite already safely stowed aboard.
Houston, Discovery.
Discovery, Houston.
Roger, we have 2 satellites latched in the bay.
Roger, that gave us a big cheer down here.
Mission 51A was a success, a dramatic example of the usefulness of man's presence in space. 51A also proved once again that plans and procedures could be altered on the spot if necessary to get the job done. NASA would put this experience into good use again in 1985 as 2 additional missions became involved in satellite rescue and repair.
Discovery Houston.
April
You're looking good for
1985, Space Shuttle Discovery is in orbit. The mission started out normally enough with Telesat 1, a Canadian communications satellite being spring ejected from the cargo bay.
Discovery Houston.
During the crew's second day in space, SYNCOM 4 was deployed. Everything seemed to be going as planned.
Outstanding. 2 for 2.
The crew watched expectantly for the omnidirectional antenna on top of the satellite to raise to its standing position. However,
Houston, this is Discovery. We are watching the SYNCOM. The Omni antenna is still down.
Roger, Ray. Any kind of visual assessment you could give us of the SYNCOM spin up, etc., would be appreciated. We sure like any kind of good photos you can be taking at this time, too.
Yes, sir. The Omni is still down, and we're trying to watch the spin up.
About 45 minutes after deployment from the cargo bay, the firing of SYNCOM's perigee kick motor, which would start the satellite on its way to geosynchronous orbit, did not occur.
Apparently, a switch lever on the side of the satellite didn't activate when it came out of the cargo bay. So the people on the ground began to search for a way to trip that switch. One thing they had to keep in mind was that anything that we used to actually trip the switch had to be constructed from materials that we already had on board. And what they came up with was a couple of homemade devices, and we called them the lacrosse stick and the fly swatter. And they were basically made out of some metal tubing, some plastic book covers that we had on our checklist, a metal window shade, also some wire and some gray tape that we carry on board on every flight. The devices were going to be attached to the end of the robot arm. The whole procedure for making and using these devices went through a trial run on the ground. They did runs in the weightless environment training facility where the spacesuit procedures are tested. They did some work in the arm training facility with a mock-up of the SYNCOM satellite to see actually what would work. The mission was extended for a couple of days so we could rendezvous with the satellite. And during that time, Mission Control sent up a massive amount of information on the teleprinter. That included detailed instructions for building the fly swatter and, in fact, an entire rendezvous checklist.
A lot more fun than listening to bell sound.
Mission specialists Jeff Hoffman and David Griggs prepared for the EVA, while mission specialist Ray Seddon maneuvered the robot arm into a convenient place for Hoffman and Griggs to attach the fly swatter devices to the end effector.
1082, Jerry.
Howdy, we got a good picture of you.
Okay.
Jeff, I want to caution you that you're getting your pliss and maybe the helmet into the fly swatter there. You got to be careful that you don't get those things bent up.
Oh, okay. I'll try to move around. Easy, hold it, Jeff. Don't do anything. Okay.
And Discovery Houston, you just got a round of applause. Thanks for the work.
Hey, you're welcome.
The next day, Commander Carol Bodko and pilot Don Williams maneuvered the shuttle into position for the rendezvous with SYNCOM.
I guess there was some question as to whether the arm could be used in this way. We were using some rather primitive tools on the end of the arm to see if we could tug on a separation switch and activate a satellite. We counted at least 3 really good whacks at it, but then the window of time in which correct activation was possible ended. Since we'd made hard contact with the switch, we had to back off from it in case the booster rocket was going to fire. The Omni antenna never did come up, but NASA decided that further attempts would not be made to try and trip the switch.
On the ground, Hughes Aircraft Company engineers performed an extensive failure analysis during the weeks that followed Mission 51D. This analysis led to the development of 2 separate electronics units designed to activate the dormant satellite. In the months following Mission 51D, NASA and Hughes agreed to develop plans for a shuttle mission to attempt to salvage SYNCOM. This joint effort was based largely on experience gained by NASA during the Solar Max repair mission and the retrieval of Palapa and West Star.
1, ignition, and liftoff.
On August 27, 1985, Space Shuttle Mission 51I was launched. Among the objectives of this mission was to capture and repair the ailing SYNCOM satellite. On Flight Day 2, maneuvers to rendezvous with SYNCOM began. Once rendezvous operations were completed, the salvage and repair process could begin. Mission specialists James Ox Van Hoften and Bill Fisher prepared for the repair in the cargo bay, while mission specialist Mike Lounge operated the robot arm. And Commander Joe Engel and pilot Richard Covey monitored their progress. Bill Fisher describes the operation.
Ox secured himself in the foot restraints that were located on the end of the robot arm and was then moved into position to grab the satellite. Once Ox had gained manual control of the satellite, he was able to move it simply by pushing and turning it. At the controls of the robot arm, Mike carefully maneuvered Ox with the satellite in hand down toward me in the payload bay. I went to work repairing the satellite. This included some rewiring and also the installation of some electronics boxes, which would enable us to deploy the Omni antenna and also to establish communication between the satellite and Hughes ground control.
Okay, Omni deploy, fire. Omni, fire. Here she comes. Looking good. Looking good, buddy. All right. Bye. Bye-bye.
This is Mission Control. Today's extravehicular activity lasted 7 hours and 8 minutes. This broke the previous record by 1 minute.
The repairs required for SYNCOM were time-consuming, and 2 EVAs were required to complete the job. On the second EVA, we installed a new Perigee kick motor cover, removed the safe and arming pins, and set the timers on the electronics box that would eventually allow Hughes ground control to communicate with the satellite. We then installed a spin-up bar for Ox. On the end of the robot arm, Ox used the spin-up bar to position the satellite and then gave it a push to start the necessary rotations.
Okay, we copy. That's great work, everybody. I can still see the timers blinking. It works. Yeah, I do too.
The mission had been a success. Once again, NASA had demonstrated the skills necessary to efficiently work in space.
And I think we're going to find in the future that the whole concept of repairing things and maintaining them is just going to become a gradually more and more accepted idea that will make the space program just that much more robust and that much more inexpensive. It will cut some of the expense in the space program.
Experiences gained on Skylab and these space shuttle missions are the foundation on which space station operations of the future will be built. With the combination of a manned base and automated systems, the servicing of satellites will become routine, as will the deployment and operation of scientific instrument platforms. Capabilities not yet dreamed of, a future within our reach, as we continue to build towards new heights.